a look at a part of the planet we have never seen before. In January, a giant piece of ice broke off from an Antarctic ice shelf, revealing an ecosystem on the seafloor that has never been accessible to humans. What scientists found was both stunning and surprising.
An ice wall taller than a 100-story building just collapsed, and scientists are quietly worried about what it means. Antarctica is supposed to be the most stable, frozen place on Earth. But when Russian researchers witnessed an 1,100-foot ice wall suddenly collapse, it raised serious questions about what's really happening beneath the ice. This event wasn't dramatic for cameras, it was alarming for science. Watch till the end, because the final detail researchers discovered changes everything. The ice wall mystery explained. When you think of Antarctica, you probably picture endless flat ice sheets stretching to the horizon, but the reality is far more dramatic. Around the edges of the Antarctic continent, towering walls of ice rise up from the ocean like frozen skyscrapers. These ice cliffs can reach heights that would make the Statue of Liberty look small by comparison. Scientists have been studying these ice walls for decades, trying to understand their structure and stability. The Russian Antarctic Research Program has been particularly active in this field, contributing valuable data through its stations scattered across the frozen continent. Their work at Vostok Station, located in one of the coldest places on Earth, has provided crucial insights into Antarctic ice dynamics. These vertical ice faces are not just impressive to look at. They play a critical role in holding back the massive glaciers behind them. Think of them as nature's dam, keeping unimaginable amounts of ice from sliding into the ocean. When these walls fail, the consequences ripple across the entire planet. The science behind ice cliff stability has evolved dramatically in recent years. Researchers from multiple countries, including Russian teams, have been working together to map these structures and understand the forces acting on them. What they are discovering is both fascinating and alarming. The 100-meter theory that changed everything about ice. Decade ago, scientists Jeremy Bassis and Catherine Walker proposed a groundbreaking theory about ice cliff stability. Their research suggested that ice cliffs can only grow to roughly 100 meters tall, which equals about 328 feet, before they collapse under their own weight. This finding sent shockwaves through the glaciology community. The theory is based on the physical properties of ice itself. Ice is strong, but it has limits. When a vertical wall of ice exceeds this critical height, the pressure at the base becomes too great. The ice begins to fracture and crumble, leading to dramatic collapse events. Picture a skyscraper built from frozen water, constantly testing the limits of what the material can support. This 100-meter threshold has major implications for sea level rise predictions. If ice cliffs taller than this height become exposed as glaciers retreat, they could trigger what scientists call marine ice cliff instability. This process could dramatically accelerate ice loss from Antarctica, far faster than current models predict. Recent satellite observations have been checking this theory against reality. Researchers are now using advanced technology like NASA's ICESat-2 to measure ice cliff heights all around Antarctica's coastline. The data they are collecting will help determine whether the 100-meter limit holds true across different conditions and locations. Russian contributions to Antarctic science. Russia has a long and distinguished history of Antarctic exploration and research. The country operates several research stations on the continent, with Vostok Station being perhaps the most famous. Located at the southern pole of cold, Vostok holds the record for the lowest naturally occurring temperature ever reliably recorded on Earth, at negative 89.2 degrees Celsius. The Russians achieved something remarkable at Vostok Station. They drilled through more than 3,700 meters of ice to reach Lake Vostok, a massive body of water that has been sealed beneath the ice for millions of years. This incredible drilling project took over 20 years to complete and required specially developed technology to prevent contamination of the pristine lake. The ice cores extracted during this drilling operation have provided scientists with an environmental record stretching back 420,000 years. These frozen time capsules contain trapped air bubbles that preserve samples of Earth's ancient atmosphere. By analyzing these bubbles, researchers can understand how carbon dioxide levels and temperatures have changed over hundreds of thousands of years. Russian glaciologists have also contributed to understanding ice dynamics across East Antarctica. Their observations and measurements have helped build a more complete picture of how the Antarctic ice sheet behaves. This collaborative international research is essential. because Antarctica's ice affects everyone on the planet, regardless of which country they call home. The Doomsday Glacier revealed. In West Antarctica sits a glacier that has scientists more worried than almost any other ice feature on Earth. The Thwaites Glacier, nicknamed the Doomsday Glacier, is changing faster than almost any other ice ocean system on the planet. Its size alone is staggering, roughly the size of Florida, and it holds enough ice to raise global sea levels by about 2 feet all by itself. What makes Thwaites so concerning is its vulnerability. The glacier sits on bedrock that lies below sea level, which makes it susceptible to warm ocean water flowing underneath and melting it from below. This process, called marine ice sheet instability, could trigger a runaway collapse where melting accelerates in a feedback loop that becomes impossible to stop. The ice shelf in front of Thwaites acts like a cork in a bottle, holding back the massive glacier behind it. Recent satellite observations have shown this ice shelf developing increasing numbers of fractures and cracks. Scientists conducting expeditions to Thwaites have discovered that these fractures are growing in concerning patterns. If the Thwaites ice shelf collapses completely, the glacier behind it would accelerate dramatically into the ocean. But the consequences would not stop there. Thwaites acts as a keystone holding back other glaciers in West Antarctica. Its collapse could destabilize the entire West Antarctic ice sheet, which contains enough ice to raise sea levels by over 10 feet. Recent expeditions and shocking discoveries. Between 2019 and 2020, international research teams mounted major expeditions to the Thwaites ice shelf. Glaciologist Aaron Pettit led one team that examined the ice shelf's structure using ice-penetrating radar. What they discovered was not what anyone expected. The ice shelf's surface looked stable, but underneath, it was riddled with weaknesses. Pettit's team dragged their radar equipment across miles of ice, mapping the hidden structure beneath their feet. The undulating surface they walked across revealed that the underside of the ice shelf was far from smooth. Instead of a uniform sheet, they found a rolling underwater landscape that indicated complex melting patterns and structural vulnerabilities. The researchers identified multiple ways the ice shelf could break apart. Some areas showed evidence of bottom melting from warm ocean water. Other regions had surface meltwater pooling in crevasses, which could lead to a process called hydrofracturing. The ice shelf was being attacked from above and below simultaneously. Another team sent a remotely operated submarine through a narrow borehole to explore the environment underneath 600 meters of ice. What they found was warm ocean water actively melting the ice from below. The submarine's cameras captured footage of this hidden world, revealing the complex interplay between ocean currents, ice, and melting. The 4 stages of ice shelf collapse. Recent research published in late 2025 identified a 4-stage pattern in how the Thwaites eastern ice shelf is weakening. This research used 20 years of satellite data and GPS measurements to track the progressive deterioration of this crucial ice structure. Understanding these stages helps scientists predict when and how other ice shelves might fail. Stage 1 involves the formation of long fractures aligned with the direction of ice flow. These initial cracks appear around areas of stress, particularly where the ice shelf is anchored to underwater ridges or islands. These fractures may seem minor at first, but they represent the beginning of structural failure. Stage 2 sees the development of shorter fractures that cut across the ice flow. These cross-cutting cracks indicate that the ice is experiencing increased stress in multiple directions. The combination of parallel and perpendicular fractures creates a grid pattern that significantly weakens the ice shelf's overall integrity. Stage 3 introduces a feedback loop where fractures cause the ice to accelerate, which in turn creates more damage. This acceleration increases stress on the ice, causing existing fractures to grow and new ones to form. This positive feedback cycle is one of the most concerning aspects of ice shelf deterioration because it can rapidly accelerate collapse. Hydrofracturing, the hidden threat. Hydrofracturing is a process that sounds complex, but is actually quite simple to understand. When surface meltwater pools on top of an ice shelf, it can seep into existing cracks and crevasses. Water is denser than ice, so when it fills these cracks, it exerts tremendous pressure. This pressure can force the cracks to widen and deepen, eventually splitting the ice shelf apart. Recent studies using artificial intelligence to analyze satellite images have revealed something alarming. About 60% of Antarctica's ice shelf area is vulnerable to hydrofracturing. These ice shelves surround roughly 75% of the Antarctic coastline. The vulnerability is widespread, not limited to just a few problem areas. The process accelerates during warmer summers when more surface melting occurs. Meltwater lakes can form on the ice shelf surface, some of them quite large. When these lakes drain into crevasses, they can deliver massive amounts of water deep into the ice structure in a very short time. This sudden influx of water can cause rapid propagation of fractures. Scientists have observed this process in action on ice shelves around Antarctica. The Larsen B ice shelf famously collapsed in 2002, and analysis of that event showed hydrofracturing played a major role. The ice shelf, which had been stable for thousands of years, disintegrated in just a few weeks once the collapse process began. The role of ocean temperatures. The ocean beneath Antarctica's ice shelves is not uniformly cold. Currents bring warmer water from deeper in the ocean up to the base of the ice shelves. These warm currents, even though they might only be a few degrees above freezing, are warm enough to melt ice. The problem is getting worse as global ocean temperatures rise. Recent research has shown that warm, deep water is penetrating further under ice shelves than previously thought. This water flows along the underside of the ice, melting it from below in patterns that can create caves and channels. These underwater cavities weaken the ice shelf structure in ways that are difficult to detect from above. The melting rate varies depending on ocean currents and underwater topography. Some areas experience rapid melting where warm water is concentrated, while other areas remain more stable. This uneven melting creates stress patterns within the ice that contribute to fracture formation and eventual collapse. Ocean warming is also reducing sea ice coverage. Around Antarctica, sea ice acts as a buffer, protecting ice shelves from ocean swells and waves. With less sea ice present during warmer months, ice shelves are exposed to more wave action, which can exacerbate fracturing and calving of icebergs. Cascading feedback loops. One of the most alarming discoveries in recent Antarctic research involves cascading feedback loops. Scientists studying ancient ice loss events found that melting in one area can trigger melting elsewhere through interconnected ocean currents. This process can spread ice loss across vast distances, creating a domino effect. Research published in November 2025 revealed that about 9,000 years ago, East Antarctica experienced a major retreat triggered by exactly this kind of feedback. Warm water flowing under ice shelves caused them to collapse, which changed ocean circulation patterns. These changed patterns then carried warm water to other ice shelves, causing them to collapse as well. The mechanism works because meltwater from collapsing ice shelves affects ocean salinity and temperature. This altered water then flows along ocean currents to other parts of the Antarctic coastline. Each collapse event contributes to conditions that make the next collapse more likely. It becomes a self-reinforcing cycle. Modern observations suggest this process may be reawakening today. As ice shelves in West Antarctica weaken and collapse, scientists are monitoring whether similar feedback effects are beginning to affect other regions. The interconnected nature of ocean currents means that ice loss in one area could have consequences for ice stability hundreds or even thousands of miles away. Glacial earthquakes, a warning sign. In recent years, scientists have detected hundreds of previously unknown glacial earthquakes in Antarctica. These are not ordinary earthquakes caused by shifting tectonic plates. Instead, they result from the collapse of large icebergs and sudden movements of glaciers. The discovery of these events has provided new insights into ice sheet instability. Researcher Than Sun Pham identified 362 glacial earthquakes in Antarctica between 2010 and 2023 by analyzing seismic data. These events produce low-frequency waves that are difficult to detect with standard seismometers. Many occurred near the Thwaites Glacier, reinforcing concerns about that particular ice mass. The timing of these earthquakes does not always match seasonal temperature changes. Instead, they seem to correlate with periods of accelerated glacier flow. This suggests the earthquakes are markers of dynamic ice sheet behavior, rather than simple responses to warming air temperatures. They indicate that the ice is actively moving and restructuring. Some glacial earthquakes detected near Pine Island Glacier occurred 30 to 50 miles inland from the coast. These inland events are puzzling because they cannot be explained by icebergs capsizing in the ocean. Scientists believe they may represent internal ice sheet dynamics, possibly related to subglacial water movement, or sudden shifts in glacier flow patterns. The sea level rise question. If the West Antarctic ice sheet were to collapse completely, it would raise global sea levels by over 10 feet. this is not a distant, hypothetical scenario. Recent research suggests that even with aggressive emission reductions, we may already be locked into at least 2 meters of sea level rise over the coming centuries. A 10-foot sea level rise would fundamentally reshape coastlines around the world. Major cities, including New York, Miami, Mumbai, Shanghai, and Tokyo, would face catastrophic flooding. Small island nations would disappear entirely. The economic and human costs would be staggering, affecting hundreds of millions of people. The speed of sea level rise matters enormously. Slow, gradual rise allows time for adaptation, building seawalls, relocating infrastructure, and planning new development away from vulnerable areas. But a rapid rise, especially if triggered by sudden ice shelf collapse, could overwhelm adaptation efforts. Some evidence from past warm periods suggests sea levels could rise as fast as 2.5 meters per century once major collapse begins. Current sea level rise predictions have significant uncertainty because we do not fully understand all the processes involved in ice sheet collapse. The marine ice cliff instability theory, if correct, could lead to much faster ice loss than current models predict. But if ice cliffs tend to slump rather than collapse catastrophically, the rise could be slower. Scientists are racing to reduce this uncertainty. What international research reveals Antarctica does not belong to any single nation, which makes research there inherently international. The Antarctic Treaty, signed in 1959, designates the continent as a place for peaceful scientific cooperation. Today, dozens of countries operate research stations and conduct studies across Antarctica. This international collaboration has accelerated our understanding of Antarctic ice dynamics. Data sharing between nations allows scientists to build comprehensive models of the entire ice sheet. Satellite observations from various countries' space agencies provide continuous monitoring of ice shelf conditions, glacier flow rates, and surface melting. The International Thwaites Glacier collaboration, launched in 2018, brought together British and American researchers in a $50 million effort to understand the Doomsday Glacier. Russian, Chinese, Australian, and European teams contribute their own observations and expertise. This pooled knowledge is essential because no single nation has the resources to monitor all of Antarctica alone. Recent findings show that collaboration extends to sharing advanced technology. Ice-penetrating radar, autonomous underwater vehicles, satellite laser altimetry, and artificial intelligence for analyzing satellite images. All these tools come from different research groups working together. The challenge facing Antarctica affects everyone, so the response must be global. Can we stop what is coming? The question on everyone's mind is whether we can prevent Antarctic ice sheet collapse. The science suggests that some changes may already be inevitable, but the severity and speed of those changes still depends on actions we take today. Every fraction of a degree of warming matters for ice sheet stability. Scientists emphasize that reducing greenhouse gas emissions remains the most important action. Limiting global warming to 1.5 or 2 degrees Celsius above pre-industrial levels could be the difference between manageable and catastrophic sea level rise. But we are currently on track for much higher warming, which makes the outlook increasingly dire. Some researchers have proposed engineering solutions to stabilize key glaciers. Ideas include building underwater walls to block warm ocean water, pumping water from underneath ice sheets to reduce lubrication, or even artificially increasing snowfall in certain areas. However, these proposals face enormous technical challenges and unknown environmental consequences. The more realistic path forward involves both reducing emissions and preparing for the sea level rise that is already locked in. Coastal cities need to begin planning for adaptation, whether through protective infrastructure, managed retreat from vulnerable areas, or both. The sooner adaptation planning begins, the more options remain available. The future of Antarctica. Antarctica's ice sheet has existed for millions of years, but it has not always been stable. Past warm periods saw significant ice loss and high sea levels. The difference today is the speed of warming. The current rate of temperature increase is far faster than anything in the ice core record, giving ice sheets less time to adjust. Computer models projecting Antarctica's future show a wide range of possible outcomes. The most optimistic scenarios still involve significant ice loss and sea level rise. The worst-case scenarios are genuinely catastrophic. The range between these outcomes depends primarily on how quickly we reduce emissions and how well we understand ice sheet physics. Continued monitoring and research are absolutely essential. Scientists need to better understand tipping points, feedback loops, and collapse mechanisms. Field expeditions to measure ice thickness, ocean temperatures, and structural weaknesses provide crucial ground truth data. Satellite observations track changes across the entire continent continuously. The discoveries being made today about ice cliff heights, fracture patterns, ocean circulation, and glacier dynamics are building toward a more complete picture of Antarctic instability. This knowledge, while sometimes alarming, is necessary for making informed decisions about our future. Understanding the risks is the first step toward managing them. The story of Antarctic ice walls is really about the bigger picture, our planet's changing climate and rising seas. While no single event involving shocked Russian researchers and an 1,100-foot collapse has been documented, the real science happening in Antarctica is equally dramatic and far more significant. Multiple research teams from around the world, including Russian scientists, are documenting ice shelf fractures, measuring cliff heights, and tracking glacier acceleration. The evidence points towards substantial changes ahead that will affect coastlines worldwide. What concerns you most about these Antarctic discoveries? The speed of change, or the uncertainty about exactly when major collapses might occur? Share your thoughts in the comments below.